to the internet these days, this is basically what you'll see when it comes to the seasons. You'll typically see Earth like this, and this will be tilted the way it is shown, and then they'll slide this same picture over here and the tilt will be facing the same direction. If that could happen, you would get a seasonal variation, because when the sun is, I guess I've got it, this would be the southern hemisphere facing inward, northern hemisphere facing out, so this would be winter in northern hemisphere. And over here you would have a summer orientation, because north is facing toward the sun. However, that cannot possibly happen, because anything that's actually rotating, its orientation will remain constant throughout its orbit. And that's what the problem with these two-dimensional drawings are, is that they're just two-dimensional drawings. So I've got this highly exaggerated, just so it's easier to see what's going on. We've got the Earth tilted towards the sun. That'd be the northern hemisphere. The N, it's really just to show how the orientation is. So what we can see here is that the N is oriented and facing the sun. Now let's turn it on. Now we're rotating, now we're orbiting. And this is a top view. I'll show a side view here in a second. But as you can see, the orientation always stays in its original position. There's no mechanism for the orientation to change the way we see in the animations. The only way this could end up being the other way around, as we see in the animations, or like I showed on the whiteboard, is you'd have to introduce a wobble into the system. And we're told this is there's three motions of Earth. It's the daily rotation on its axis, 1, and the rotation around its sun, 2, the yearly rotation, and 3, the great year, which is supposed to be a wobble. So there's only two orbital motions in a year, and that's what we're showing here. One complete revolution would equal a year. And as you can see, there's no variance in the orientation between the Earth and the center that it's rotating about. How could there be? So this is fundamental. If they can trick you into believing that the orientation will somehow change as anything orbits its center, then you're primed to believe everything that follows behind that notion. And so here we are, we've dispelled the notion that there's any way at all a planet could change its orientation. I hope that demonstrates thoroughly that the seasons cannot in any form or fashion be caused by the Earth rotating around the sun and changing its orientation. It won't happen. So what will happen? Let's take a look. Here's the representation of what we see in the diagram, but in this case the sun will be orbiting Earth. So in this position, that's the first position on the whiteboard, the southern hemisphere is facing the sun. So at this point in time, this would be the winter solstice in the northern hemisphere. The northern hemisphere is pointing away from the sun, and so it's winter time in the north. In the southern hemisphere is pointing toward the sun, so we know that it's summer in the southern hemisphere. Now let's go to the second position. Now in the second position, from above we can see the sun is lateral with the equator on Earth, and this is equivalent to the spring equinox in the northern hemisphere and fall equinox in the southern hemisphere. Now in this third position we can see the Earth is still in its same position. However, the northern hemisphere is facing the sun, as the sun has made its way 3/4 of the way around its orbit. And now it is the summer solstice. This will be the highest point the sun will be in the sky in the northern hemisphere, the lowest in the southern. And this will indicate southern hemisphere pointing away from the sun, northern hemisphere pointing toward the sun. And now the fourth position, the sun is parallel with the equator, and so clearly this is a equinox, and this would be the fall equinox in the northern hemisphere and the spring equinox in the southern hemisphere. This is the day of the year where day and night are exactly the same length. While I was filming the turntable model, I thought about something. So if this is the orientation of Earth in December, and it travels all the way around here and somehow returns to June, so 6 months apart, and if that were the case, then this is 149 million miles supposedly from here to here, and 149 million, so 150 million miles, so 300 million miles approximately distance. So you've got Earth here pointing at Polaris, and then you got Earth here pointing at Polaris. So what does that tell us about the size of Polaris? Well, first of all, they'll say it's so far away that it's the distance is just so far away. Well, okay, if the distance is so far away, then how do we know it's even pointing at Polaris? It could be pointing at a billion different stars if everything's so far away. So what it really shows is that Polaris is as big as the diameter of Earth's orbit, which then leads to the question, if Polaris is that huge, then how does Vega ever become a pole star? Because Polaris is always there, it's so huge. So when does Vega assume its position? So if anyone can answer that question, I'm all ears. Let's say that here's Polaris, here is Polaris, okay? So you can see the pole pointing at Polaris. But if this thing stayed consistent the way it should be, as I've shown in the model, it'll end up over here like that. it's always gonna have the same pole facing the sun in reality. So this would be a different pole star. And so we'd have a new pole star certainly every 6 months and probably about every 2 weeks as the Earth circled on that huge 107,000 kilometer per hour journey around the sun. So that's their problem. That's the reason they have to keep it. That's the reason they have to keep it in the same position no matter where it's at in its orbit, which is easy to do when you have a cartoon and a flat piece of paper. But if those stars were so far away that, well, they could just be pointing at any star at all. I mean, just pick one. I hope this is food for thought for some of you folks.